What if the very foundation of everything we think we know about the cosmos is wrong? Seriously, for decades we've relied on this incredibly successful map of the universe. But brand new, shocking data coming in from our most powerful telescopes is telling us that our map is broken. And now a new theory is bubbling up that might just rewrite the cosmic rules from the ground up.
So here's the game plan for this explainer. First, we're going to investigate the crime scene. We'll look at the cracks that are starting to show in our standard model of cosmology. Then we'll meet the main suspect, this radical new idea of a dynamic vacuum. We'll see how it might just solve the very puzzles that have been stumping everybody, see how it stacks up against the competition, and even how it could help with a huge argument that's been raging in cosmology. And then finally, we'll look at what all this means for the universe's next chapter. All right, first up, let's dive into those cracks. Why is the map of the universe that we've trusted for so long suddenly failing us? Okay, so for years, our guide to the cosmos has been what's called the lambda-cold dark matter model. We just call it ΛCDM for short. And you have to understand, this model has been the absolute bedrock of cosmology. It's been wildly successful, explaining everything from the afterglow of the Big Bang to how galaxies clump together. It's been our gold standard. And that's exactly what makes these new problems so alarming. And the trouble didn't start a long time ago. We're talking very recently. In March of 2025, the Dark Energy Spectroscopic Instrument, DESI for short, dropped its data from mapping an incredible 14 million galaxies. And the results? They showed some really major inconsistencies with our standard model. Then, that same month, a brand new space telescope called Euclid sent back its first preview, and guess what? It confirmed DESI's strange findings. By early 2026, it was clear these anomalies weren't just going away. In fact, they were getting stronger. So, what did this incredible new data actually find? Well, it pointed to three huge system failures. First, dark energy. That mysterious force that's pushing the universe apart faster and faster. It doesn't seem to be constant like we thought. It looks like it's actually changing over time. Second, the way huge things like galaxy clusters grow is happening slower than the model says it should. And third, well, this is the real bombshell. When you use the standard model with this new data, it calculates a mass for these tiny particles called neutrinos that is negative. Look at this number, negative 0.156 electron volts. This is the smoking gun. Getting a result like this is like stepping on your bathroom scale and it tells you that you weigh negative 20 pounds. You wouldn't think, oh no, I don't exist. You'd know with absolute certainty that the scale itself is fundamentally broken. And that's what this number is telling cosmologists. ΛCDM, our trusted scale for the universe, is broken. So how can mass be negative? The short answer? It can't. The laws of physics just don't work that way. And what that means is, we can't just tinker with the old theory anymore. We might need a whole new one. And that crisis, well, it opens the door to a radical new idea that could fix everything. It's called the dynamic vacuum, and it all starts with a simple question. What if the nothingness of empty space isn't really nothing at all? So let me introduce you to the new theory on the block, dynamic vacuum field theory, or DVFT. It proposes something that is just incredibly elegant. It says that the vacuum of space isn't empty. It's actually a single, complex, energetic field. And from the behavior of this one field, three of the biggest mysteries in physics could just naturally emerge. Dark energy, the effects of dark matter, and even the mass of particles. One single field to potentially explain it all. So how in the world does this work? Well, let's skip the really heavy math and just think of it like this. Picture the vacuum like the surface of a pond. The theory says this field has two key parts. First, there's the amplitude. You can think of this like the average water level of the pond. It's the baseline energy of space. But then you have the phase, and these are the ripples and waves moving across that surface. DVFT says that the complex dance between this baseline energy level and all its little ripples is what's actually driving the entire evolution of the cosmos. Okay, now for the really cool part, the payoff. Let's see how this brand new idea of a dynamic vacuum doesn't just patch the old model, but seems to perfectly explain the very problems that broke it in the first place. Remember that impossible, physically nonsensical negative mass for neutrinos? On the left, you see the error that the old model, ΛCDM, spits out. But now look at the right. DVFT, using its own rules, its own internal logic, actually derives a perfectly sensible, positive mass for neutrinos of around 0.03 electron volts. It doesn't just fix the problem, it calculates a real-world value right from its own foundation. And it's the exact same story when we look at dark energy. The old model just assumed it was constant, which we now know from the new data isn't true. But DVFT, it actually predicts that dark energy should change over cosmic time. And I don't mean just vaguely. The theory's equations churn out the exact parameters for this evolution, those W0 and WA values you see there, that our telescopes are now observing. It is a stunning direct hit. But here's where the theory makes its most audacious claim. What about dark matter? For decades, we've been hunting for some mysterious, exotic particle. DVFT comes along and says, what if there is no dark matter particle to find? Instead, it suggests that the vacuum field itself can bunch up, it can cluster, and it can warp spacetime, creating the exact same gravitational effects we've been blaming on dark matter. The culprit might have been hiding in plain sight this whole time, as the fabric of space itself. So, DVFT sounds pretty good, right? It seems to solve these huge problems. But how does it really stack up against the competition? Let's put it head-to-head with the old model and some of the other alternative ideas out there. Okay, this right here is the tail of the tape. That observation column, that's reality. That's what our telescopes actually see. Now just look at the DVFT prediction column right next to it. For dark energy's behavior today, why not? Bang, a perfect match at negative 0.78. For the neutrino mass, it solves that impossible negative value. For the S8 parameter, which is just a measure of how clumpy the universe is, another direct hit. And for dark matter, it predicts 0, because it's just an effect of the vacuum. No other model out there can match reality so precisely across so many different, independent measurements, all from one single unified idea. All right, next up, let's talk about one of the biggest arguments in all of cosmology, the Hubble tension. It's a huge disagreement over how fast the universe is expanding, and this new theory might just offer a way out. So what is the Hubble tension in simple terms? Well, it's a giant cosmic puzzle. When we look at the light from the early universe, from something called the cosmic microwave background, we calculate one speed for the universe's expansion. But when we look at things in the modern universe, like exploding stars, we get a different speed, a significantly faster one. Both measurements are incredibly precise, but they don't agree, and it's been a massive headache for years. And this is where DVFT offers a potential olive branch. This chart shows you the whole conflict. On the left, in blue, you have the slower value from the early universe. On the right, in red, the faster value from today. And look what's sitting right there in the middle, in green. That's the expansion rate predicted by DVFT, landing at 70.6. It doesn't fully solve the problem, but it lands beautifully between the two warring sides, and it seriously reduces the tension between them. And all of this brings us to our final section, the universe's next chapter. We've seen what this theory can explain, but what does it predict for the future? And, most importantly, how can we actually go out and test if it's right? This quote from the theory's author, S. Thorway, just nails the core idea perfectly. It says that dark energy, dark matter, and neutrino mass, maybe they aren't separate, disconnected puzzles we have to solve one by one. Maybe they are all just different faces of a single underlying thing, the dynamic vacuum field itself. It's an absolutely incredible claim of unification. But here's the crucial part. This isn't just a cool story or philosophy. This is real, testable science. DVFT makes very specific, very bold predictions. It forecasts things like a 5% extra gravitational lensing effect on small scales and about a 10% change in the cosmic microwave background on large scales. These are concrete, measurable signals we can actually go out and look for. And with the next big data dumps from DESI and Euclid expected in late 2026, we might not have to wait very long for an answer. Which really just leaves us with this one final mind-bending question. For almost a century, we've been searching for answers by looking for exotic new particles and mysterious new forces. We've looked out to the infinitely large and down to the infinitely small. But what if the solution was never really out there at all? What if the biggest secrets of the entire cosmos have been hiding right under our noses the whole time, woven into the very fabric of what we've always dismissed as just empty space?